Ever wonder what would happen if we could rewind time and change just one thing? Like, what if that new policy had never been passed? Or what if that conflict never started? These what-if questions are called counterfactuals, and they're the secret sauce behind some of the most exciting advances in data science today. But here's the thing, we can't actually time travel to test these scenarios. So how do scientists figure out what would have happened? The answer lies in causal inference, a fancy way of using data to estimate hidden outcomes. Think of it like solving a mystery with only partial clues. You don't see the whole story, but you can piece it together using math and smart models. The problem? Traditional methods are like using a ruler to measure a rainbow. They work for simple cases, but when you're dealing with data that changes over both space and time, like tracking how a disease spreads across cities or how a forest burns over months, they fall apart. That's where this new research steps in. They're using a type of AI called a transformer, the same tech that powers your favorite chatbots. But instead of just understanding language, they've adapted it to tackle spatiotemporal data. Imagine a detective that can read clues across a map and a timeline. This model doesn't just look at today's data, it connects the dots between past, present, and future. Here's how it works. First, they use a convolutional neural network, CNN, to calculate propensity scores, like a weather forecast for treatment likelihood. If a policy is more likely to be implemented in a certain region, the CNN spots that pattern. Then the transformer takes over, learning how events intensify over time and space. It's like teaching a computer to predict how a wildfire spreads based on wind, fuel, and geography. But here's the catch, no model is perfect. The researchers broke down their estimation errors into two parts. Let's call them E1t and E2t. Think of them as two types of noise in the system. First, E1t is the error from the model's predictions. The team showed that as they collect more data, this error starts to act like a normal distribution, the classic bell curve. Why does that matter? Because the bell curve is predictable. It means the model's mistakes become consistent over time, making the results more reliable. It's like training a puppy. The more you practice, the fewer random jumps it makes. Then there's E2t, the trickier error. This one measures the gap between the model's smoothed predictions and the actual outcomes. The researchers proved that as data grows, this error shrinks to zero, like a fading echo. The more information you have, the quieter that noise gets. But how did they figure this out? They used math that's as elegant as it is complex. Concepts like martingale difference series, which are like random steps that don't depend on the past, and the central limit theorem, which says even chaotic systems tend to form a bell curve over time. By combining these tools, they showed their model isn't just guessing, it's building a trustworthy map of possibilities. And the real-world impact. In simulations, their model outperformed older methods, showing less bias. But the real test? Applying it to real data on conflicts in Colombia from 2002 to 2022. They found that longer, more intense conflicts led to more forest loss, a clear link that could help policymakers protect ecosystems better. So why does this matter? Traditional methods are like using a magnifying glass in a storm. This new approach uses AI to capture the full picture, accounting for both where and when events happen. It's not just about better predictions, it's about understanding the hidden connections in our world, from climate change to social dynamics. Next time you hear about a conflict or a policy change, remember, behind the scenes, scientists are using tools like transformers to ask, what if? And uncover the stories data can't always tell on its own. Thanks for watching, stay curious.